Alrighty, let's do some implicit differentiation. Now, what the heck is implicit differentiation? Well, look at these. Are you used to functions where x's and y's are all mixed up? Aren't you used to y equal functions? That's kind of what you plug into graphing calculators, and it's the most common that you're used to. Well, when you have y equal functions, those are called explicit. When everything's mixed up, they call it implicit. So you see how both these are all kind of mixed up? These are called implicit equations. They are not functions. They are equations that, the vertical line plus test does not apply to them. Anyways, in order to differentiate these, you don't want to try to get y equals. That would be kind of a bear. Okay, let's get y equals. Oh, that could be really ugly. Yes, it could. So don't mess with getting y equals. We simply take the derivative of everything where it's at, one by one. And we do a little chain rule as well. You'll see it come about. So, ready? Here we go. What we do for taking the derivative of this is we just derive it one by one. Ready? What is the derivative of this first piece? Well, that's just going to be 6x. Hopefully your basic power rule is pretty strong. All right, what's the derivative of tangent y? Or negative tangent y? Well, wouldn't that be just negative secant squared? Negative secant squared y? But, don't you have to chain rule the inside? What's the derivative of y? Oh, the derivative of y is y prime. Oh, or dy dx. Well, why didn't I put x prime? What's the derivative of x? It's 1. Because what we're doing is we're taking the derivative of all this in respects to x. So when I take the derivative of all this in respects to x, right here, that just derivative of x is 1. But the derivative of y is y prime. Okay, one way to think of that, this could help you just understand the basic idea. If I take the derivative of dx of x, isn't that basically dx over dx, which is 1? But if I'm taking the derivative of y, isn't that dy dx, which is y prime? All right. When I take the derivative in respect to x of x, I get 1. Dx over dx, anything over itself is 1. If I take the derivative of y, I get dy dx. And I like putting y prime. Instead of writing dy dx, y prime is just easier for me. Don't think that's y to the first power. Some people think, y to the first power? No, it's not y to the first power. Sorry. Okay, what's the derivative of 4y? Well, the derivative of 4y is 4 times y prime. Don't forget that y prime. Chain rule. Be careful. All right, so I took the derivative. I'm done. No, not really. You need to get y prime by itself. You want your answer to be y prime equals the derivative of y equals blank. So how do I get y prime all by itself on one side of this funny looking equation? Well, what I'm going to do is I'm going to get all the y primes to one side to start with. So let's start off with adding secant squared y times y prime. I'm going to add that over, so that's going to add over to here, giving you secant squared y times y prime. Let that cancel out. And what you now have is 6x equals 4y prime plus secant squared y, y prime. Okay. Now what? Well, what do you think? Well, if I want to get y prime by itself, well, do you see a GCF of y prime on both of these? Greatest common factor? So watch this. Could I simply pull a y prime out of both of these? When I pull a y prime out, doesn't that leave you 4 and secant y squared? Yeah, it does. Okay, but what does pulling a GCF, greatest common factor of y prime out, how is that going to help me get y prime by itself? Do you see it? Couldn't I divide both sides by this and get y prime isolated by itself? Watch this. Divide by the secant squared y, gone. divided over 4 plus secant squared y. And what do you notice? I got y prime by itself. Y prime is equal to the 6x over 4 plus secant squared y. I have the derivative of y. Y prime equals, bam, I got it. I'm done. So what did we do? Let's kind of hash through the concept again. You got to take the derivative of everything where it's at. Be careful to, whenever you take a derivative of y, chain rule y prime out, because you have to derive the outside and then derive the inside. Derive the outside of 4y and then derive the inside. Then, once we get everything differentiated, then I want to add or get the y primes to one side. Doesn't matter what side the y primes are on, just get them to one side. Then pull a GCF of y prime out. There's almost always going to be GCF of y prime you pull out. And then to get y prime by itself, you divide it over, divide the excess or the other piece over, and bam, you'll get y prime by itself. And that would be the derivative of this implicit equation. All right, so evaluate this derivative at -3, 2. So we take the derivative, but if I want to evaluate it at -3, 2, aren't you going to take the derivative and plug in the coordinate xy? Now when we did explicits, when I took the derivative, I just plugged in the x value. But when I take the derivative of this, won't I have x's and y's, so do I need both to find the derivative at a specific point? Implicits need a point, not just an x value, to find the derivative at a specific point. So here we go. Let's do this derivative, all right, implicitly. You don't want to try to get y equals and do it explicits. So here we go. The derivative of y cubed is going to be 3y squared. 3 goes out front, drop the power by 1. Y prime, not y to the first, y prime. Be careful with that. Now this is going to get a little annoying. Watch this. This is product rule. Look at this one right here. This is a little tricky. I have a minus and I have a product rule. Ready? Don't I have a negative 2x times y? So what's the product rule? Be very, very careful. What's the derivative of negative 2x? Sorry, of 2x. I'll put the negative there. The derivative of 2x is 2, leave the y, plus leave the 2x, take the derivative of y. You see product rule. Derive the 2x, leave the y, leave the 2x, derive the y. Now, by the way, could I have taken that 2 and just put it out here in front and not worry about the 2? Yeah, and just done xy? You could have done that as well. There's different ways of doing it. I just, for some reason, didn't do it that way. But anyways, just watch out for this negative. It's going to be important. It might mess you up in a second. Just you got to watch this as a product rule. Many people do not see that as a product rule. They just say, oh, it's negative 2y prime. Be careful, please. Anyways, what's the derivative of 20? Well, the derivative of 20, any number derived, is 0. All right, I'm done. No, I'm not. Now, do I have to rewrite it as y prime? No, because aren't we evaluating at this coordinate? So why solve for y prime and possibly make a mistake? Can I just plug x and y in, and then once I get all the numbers plugged in, can I simply solve for y prime, the leftover? Just be careful. These parentheses are really important here. If a lot of people forget this parenthesis and forget this negative is going to distribute to both. Just pointing that out. Make sure you know this negative will distribute to both. Okay, let's plug everything, plug the x and y in, and then evaluate the derivative. So I have 3 y squared. Well, y is 2. So 2 squared, leave the y prime, minus 2 times y, which is 2, plus 2 times x, which is negative 3, y prime equals 0. You see how we're solving here? See how we can just simply plug it in? See how I do not have to get y prime by itself and then plug it in? is a lot quicker when you're evaluating not to get y prime by itself. Okay, enough said with that. What do we get here? That's 4. 3 times 4 is 12 y prime. Okay, that becomes 2 times 2, which is 4. And then what's, okay, 4, 2 times negative 3 is negative 6 y prime equals 0. All right, from there, I want to solve for y prime. So how do we get y prime and solve for it? Well, can I distribute the negative? If I distribute the negative, it looks like I have 12y prime minus 4 plus, because that's minus 4, but be careful, a negative distributes, making that a positive 6y prime equals 0. Okay, from there, what do we got here? If I get y prime by itself, let's see. Well, can't we combine the y primes? And don't I have now, would be 18 y prime minus 4 equals 0. Okay. All right. Now, all that said and done, how do I do next? I'm just solving. Could I add the 4 over? So when I add 4 over, what do we got here? We got 18y prime equals 4. Right, we're going over here. And what do we got now? What do we have now? Oh, we divide by 18. I now have the derivative of y equals 4 over 18. Can you reduce that? Well, yes, 2 goes into both. So it'd be 2 over 9. So y prime is 2 over 9. So the derivative at this point is 2 over 9. Alright, got a little squished down here, but that is how you would do it. You take the derivative, plug in the coordinate, simplify for y prime. Now, yes, could I simply have gotten y prime like this and then plug in the coordinate? Very much so. We don't have to get y prime by itself before we put the coordinate in. Alright, now when you take the derivative up here, we didn't have a coordinate to plug in, so you have to get y prime equals. Alright, once again, derive everything where it's at. Don't forget, every time you take a derivative of y, you put a y prime. Alright, if you have this, be careful. You have a product rule here. Be careful with the products and quotients. They could kind of sneak up on you. Especially trig functions. Sometimes we forget like the y prime on those and stuff. And then we got to get y prime by itself here. Here, just solve for the derivative. So the slope, basically, at this point for this equation is 2/9. That's the slope. All right, that's implicit for you. Good luck with them.